The Lattice Key-Value Store is a distributed, persistent data structure designed for reliable storage and retrieval of binary key-value pairs across multiple nodes. The system provides eventual consistency guarantees with configurable durability levels. All operations are serialized to a write-ahead log before state modification. The core abstraction presents three primary operations: put, get, and delete. Each operation includes an associated timestamp and version number for conflict resolution. The put operation accepts a key of variable length between 1 and 512 bytes and a value of variable length up to 4 gigabytes. The system assigns an internal sequence number upon acceptance. Put operations are idempotent. Identical requests with the same key and value produce the same result regardless of execution count. The operation returns a success acknowledgement containing the assigned version timestamp. Collision behavior for duplicate keys follows last write wins semantics with microsecond precision timestamp ordering. The get operation retrieves the current value associated with a specified key. If the key does not exist, the operation returns a null result with a not found status code. Get operations do not block on pending put operations. Consistency is eventual. The operation includes an optional version parameter to retrieve specific historical values. Without a version parameter, the system returns the most recent stable value. Response time is logarithmic and dataset size due to internal tree indexing. The delete operation marks a key is removed by writing a tombstone record. Tombstones persist for a configurable retention period before garbage collection removes them entirely. Retrieval of a deleted key returns a not found status identical to keys that never existed. Delete operations are synchronous. The operation completes when the tombstone is written to the log, not when garbage collection occurs. Tombstone retention defaults to 7 days and is configurable per node. The write-ahead log maintains durability guarantees by recording all mutations before memory state modification. The log is structured as a sequence of fixed-size blocks, each 64 kilobytes. Log entries include operation type, key value data, timestamp, and a 32-bit CRC checksum. The system maintains a pointer to the last acknowledged log position. Nodes may recover from crashes by replaying all log entries from the last checkpoint forward. Checkpoints create snapshots of the in-memory state and write them to disk in compressed format. Checkpoints are triggered automatically when the write-ahead log exceeds 512 megabytes or after a configurable time interval. The checkpoint process runs asynchronously without blocking client requests. During checkpoint, the system creates a read-consistent snapshot of the key-value tree. The checkpoint file includes a manifest containing the tree structure, version numbers, and a list of included keys. The in-memory index structure is a balanced B-tree with branching factor of 64. Internal nodes contain up to 63 key pointer pairs. Leaf nodes contain actual key-value data or references to value storage for large values. The tree maintains insertion and deletion invariants to ensure logarithmic lookup performance. Leaf nodes include forward and backward pointers for efficient range scanning. Tree rebalancing occurs automatically upon modification when imbalance exceeds defined thresholds. The replication subsystem maintains copies of data across multiple nodes to provide fault tolerance. The primary node accepts all write operations and broadcasts changes to secondary nodes asynchronously. Secondaries acknowledge data receipt independently. Replication lag typically remains below 100 milliseconds under normal conditions. The system uses vector clocks to detect concurrent modifications and resolve conflicts deterministically. Replication configuration specifies replica count, failure tolerance level, and acknowledgement requirements. Failure detection relies on periodic heartbeat messages between nodes. If a node fails to send a heartbeat within a 5-second window, the system marks it as unavailable. Multiple consecutive failed heartbeats trigger failover procedures. Secondary nodes can be promoted to primary status if the previous primary remains unavailable for more than 30 seconds. Promotion requires consensus from at least half of the remaining replicas. During failover, client requests may experience brief latency increases while routing is updated. The client library provides synchronous and asynchronous API variants for all operations. Synchronous operations block until the server acknowledges the request or a timeout expires. The default timeout is 30 seconds and is configurable per operation. Asynchronous operations return immediately and invoke a callback function upon completion. The library maintains connection pooling to reduce latency and improve throughput. Connection pool size defaults to 8 and can be adjusted based on expected concurrency. Request pipelining allows multiple outstanding requests to the same server concurrently. The client library buffers requests into batches of up to 1024 operations before transmission. Batching reduces network round-trip time and improves aggregate throughput. The system guarantees request ordering within a single client connection. Cross-connection ordering is not guaranteed. Pipelining behavior can be disabled by setting the batch size to 1 for strict request response semantics. Data compression is applied automatically to values exceeding 256 bytes. The compression algorithm uses deflate with compression level 6. Compressed values include a header indicating compression status. Decompression is transparent to the client library and occurs automatically during retrieval. Compression typically reduces storage size by 40 to 70% for text and JSON data. Binary data compression ratios vary widely depending on entropy characteristics. The garbage collection process runs on a background thread and reclaims storage occupied by deleted values and obsolete log entries. Collection is triggered when the storage size exceeds 80% of the configured maximum or after 24 hours of elapsed time. During collection, the system scans the index tree and identifies unreferenced data blocks. Unreferenced blocks are added to a freed list for reuse. Collection does not block client operations but may increase latency temporarily. Access control is implemented through optional API tokens included in request headers. Tokens are opaque byte sequences and are validated against a token registry on each request. Invalid or expired tokens result in authentication failure and request rejection. The system supports token expiration with configurable lifetime. Tokens can be revoked immediately or expire automatically after a specified duration. Token validation adds minimal latency as the registry is cached in memory. Monitoring and instrumentation are provided through a metrics endpoint exposing Prometheus-compatible output. Key metrics include request latency percentiles, throughput in operations per second, replication lag, and storage utilization. The system emits structured log entries for significant events including node failures, failovers, and checkpoint completion. Log verbosity is configurable from silent to debug level. Metrics are aggregated per node and globally across the cluster. Configuration is specified through YAML files loaded at startup. All parameters have documented default values suitable for typical deployments. Common configuration options include maximum storage size, replication factor, log segment size, and checkpoint interval. Runtime configuration changes are not supported. The system must be restarted. Configuration file changes are validated before application. Invalid configurations prevent startup and generate diagnostic messages indicating the problematic parameter.